Hello and welcome to another video for Calculus 1. In this video, we are going to discuss about maxima and minima. So first, let's look at two important terminology that we are going to discuss about. So the first one is absolute maximum and absolute minimum. So here's the definition. So let f be a function with a domain D that contains the number c. The function has an absolute maximum at x equals c if f of c is greater than or equals to f of x for all x in D. Means we can take the entire domain or maybe a closed interval, some closed interval D. So in that interval, so absolute maximum means the maximum value of the function. So for example, let me draw a graph here. So for example, if we have this graph, this function from A to B in that closed interval AB, so the maximum value here, you can clearly see that it is right here. There's the highest point on the graph in that interval. So let's say that is C. So f of C in this case is greater than or equals to f of x. So no matter what x value you pick in that interval, f of C is going to be the highest value or the largest value. So that is the absolute maximum for that function in that interval. Similarly, the lowest point in the entire domain or given closed interval is the absolute minimum. Now we have a term that is absolute extrema. So when we say absolute extrema, it means both max and min. Okay, so that's the combined terminology for absolute maximum and absolute minimum. So here is an important theorem. So this theorem says is f is continuous. That means there's no break on the graph. Okay, continuous on a closed interval. So it should be a close point, a point to another point here. So that's continuous on the closed interval AB. So that's, let's say, A and that's B. Then f attains an absolute maximum value and absolute minimum value on AB. So this guarantees us, okay, so this theorem says that if the function is continuous in a closed interval, then there must be an absolute maximum and absolute minimum in that interval. So it could be at the end point, it could be somewhere else in between, but there must be a absolute max and min if the function is continuous on the closed interval. Now, if the function is not continuous, does this theorem say anything? It does not say anything. If the function is not continuous, it might have an absolute max and min. It might not have. It might have only absolute max, or it might have only absolute min. But it doesn't say anything about whether it has absolute max or min when the function is not continuous. So this talks only about when the function is continuous on a closed interval, then we can guarantee that there is an absolute max and absolute min in that interval. So now, here's an example. So this is for the given function. Here we are given the graph of the function, and then we are given the interval. So it's asking us to determine whether these functions in that given interval meet the conditions of the extreme value theorem. So I'm going to say extreme value theorem as EVT. So do they meet the condition for absolute value theorem or not? Okay, and then we identify the extrema values here. So the first thing is we have to look at two things when we look at the condition for extreme value theorem. The first one is the function must be continuous, and then it must be in the closed interval. Okay, so the function must be continuous on closed interval. So let's look at the first one here. I can see that the function is continuous because there is no break here, so it's continuous, and it is continuous on the closed interval. So the interval that is given to us is -4 to 4. So from -4 to 4, we have those dots, which means the function is continuous in the closed interval. So that means yes, it satisfies the conditions of extreme value theorem. So that means if it satisfies the condition of absolute value, extreme value theorem, then we should have an absolute max and mean here. So if you look at the graph, so the highest point on the graph is this point, and the lowest point on the graph is this point right here. So the highest point is at x equals -3 and the value is 1. So here absolute max is the y value, so absolute max equals 1. And where does that occur? It occurs at x equals -3. Okay, similarly the lowest point on the graph is this one right here, so the y value for that is -4, the x value is 2, so the absolute mean is -4 is the y value. And where does that occur? It occurs at x equals 2. Okay, so that's done. So let's look at the next question here. So if you look over here, this does not meet the conditions of, so does not meet the conditions of extreme value theorem. Okay, the reason for that is this function is not continuous on the interval -5. So -5 is over here. So from here to 0 here, the function is not continuous because there's a jump here. So the reason that it does not meet the condition of extreme value theorem is the function is not continuous on the given interval. Okay. Now, as I said earlier, it does not mean, okay, if it's not continuous on the closed interval, it does not mean it won't have absolute max or mean. So it might have. So let's go ahead and check. So if you look over here from -5 to 0, we do have a maximum, the highest point here, which is 6. Okay, and that occurs at -4. So now this one has absolute max, and that value is 6 at x equals -4, but it does not have the minimum value. So if you look from here, this is a hole, so there's no minimum here. And if you go up to here, so we really can't identify where that minimum is. Okay, so it's hard to say where that minimum is, so it has no absolute minimum. Okay, so just be careful with that extreme value theorem. It only says that if the function is continuous on closed interval, it has an absolute max and absolute mean, but it doesn't say anything if the function is not continuous. So the next definition that we have here is local max and local mean. Okay, so local maximum at x equals c, if f of c is greater than or equals to f of x, is very similar to the earlier definition. Okay, when we talk about absolute max and mean, so it looks very similar for all x in some open interval. So the difference is when we are looking at local max and mean, we are looking at the open interval. That means it cannot occur at the endpoints containing c. And so, for example, let me draw a graph. Okay, so now if you look over here, if I ask you to find the absolute max, then clearly you can say it is right here. Okay, and if I ask you to say find the absolute mean, you can clearly see it somewhere here. Okay, but now if you take a small interval, for example, if I'm taking an interval here from here to here, okay, so if I take this interval, then in that interval I do have a maximum value. Okay, so this is the local max for that is small interval. Similarly, if I take this interval here, I have a maximum value here, which is local max. Okay, similarly, if I take this small interval here, then I have a minimum here, so this is local mean. And then similarly, I have a minimum value here, so this is also local mean. So we could have several local max and mean in a given interval, okay, for a function. Now, when we say absolute, so it's basically we have so many maximums. So the maximum of all the maximums is the absolute maximum. But local means we could have a maximum in a given interval that's very small and it's an open interval. Okay, so that is the difference between local and extreme. Means that's the maximum in the closed interval. There's no other maximum value. Local means there could be other maximum, but we are just looking at a small interval, and that's the maximum for that open interval. Okay, so you could have several max and several mean which are local, but there could be only one absolute max and one absolute mean. It's just like if we are talking about the mountains, so we have different mountains in different states, right? So we have the highest mountain in each state. So those are the local highest peaks. But when you talk about the highest peak in the entire country, there could be only one. So that's the absolute max. Okay. So yeah, that's this definition. And then we call, if we are taking both max and mean, local max and local mean, then we call that as local extrema. Okay. So now, in this example, we are going to identify the various maximum and minimum. So we are going to do absolute max, absolute mean, local max, and local mean. So we can clearly see we have a maximum here, and that is the absolute maximum, because that's the highest point. It's in the closed interval. It's at the end point. So absolute max equals, so the value is 5, right? The y value is 5, and it occurs at x equals 5. Okay, so that's the absolute maximum. Now we have a minimum here. That's the absolute minimum, but for that absolute minimum we can also call it a local minimum, right? So local mean could be an absolute mean, or local max could be absolute max. This is just absolute because this is at the end point. So if it's at the end point, we cannot call it local. Okay, but this one we can say both local and absolute mean, which is at whose value is -4 and is at x equals 2. And then we have this maximum here. This is local maximum. It's not the absolute maximum because we already have absolute maximum here. So that is the local max, which is the value is 4, and then it occurs at x equals -2. So now I think if you are given a graph, you should be able to figure out which is absolute max, which one is absolute mean, and which one is local max and local mean. Okay. So there's another theorem which is called local extreme point theorem. So if f has a local maximum or minimum at x equals c, and if the derivative at c exists, then f prime of c equals 0. That basically means if you have a local max or local mean at a point, then the derivative at that point is 0 if the derivative exists. Okay, if the derivative does not exist, that's a different thing. So it's basically means, so if I have a graph like this, then I have a local max here. So the derivative is 0 because the tangent line is horizontal. We talked about that when we are talking about the derivative. Again, we have local mean here, and the tangent line here is horizontal. So wherever you have local max or local mean, and if the derivative exists, then the derivative must be 0. That means it should have a horizontal tangent line at that point. And that's not true for absolute max or mean, because they could occur at the end point. Okay, so when we talk about absolute max and mean, they could occur at the end point. So at the end point, we don't have the derivative 0. So this theorem only works for local max and local mean. Okay, and then again, remember, only if the derivative exists. In that case, the derivative must be 0 when the local max and local mean occur at a point. Now, it's very important to note something here. I have put that here. So if the derivative is 0, we cannot confirm that there is a local max or mean. If there is a local max or mean, then the derivative must be 0 if the derivative exists. But just having the derivative 0 does not guarantee us that there is a local max or mean. Here is an example here. Okay, so for example, in this graph, if you look over at this point right here, you can see we have a horizontal tangent line here, and then the derivative is 0, but it does not have a max or mean here. This is not local max or local mean. Okay, so local max and local mean occurs in those turning point where the function goes from, so if it's a local max, the function comes as increasing function and it changes to a decreasing. Okay, so it rises and falls down, so that's where we have max. Similarly, it decreases and turns back as increasing, then in that point we have local mean. But here in this case the function is still increasing, so that we don't have a local max or local mean here. Okay, so now the point to note is if the derivative is zero, we cannot guarantee that there's a local max or local mean. Okay, we have to check that. And the other condition is we could have a local minimum at a point where the derivative does not exist, like the sharp turning point, sharp corner here, right? We discussed about this one when we talked about derivative, that at a sharp corner the derivative does not exist, and then we could have a local mean or local max there. Okay, so for example, if you have that absolute value function, you have a local mean. If you have absolute value function in the other direction, then you have local max, but the derivative does not exist. So basically, local max and mean could occur at a point where the derivative does not exist and where the derivative is zero. Again, it does not guarantee when the derivative is zero. We have to do other tests to confirm that there is a local max and mean. Okay. Now, there's an important thing that we use in order to find the absolute max and mean. So that number is called a critical number, and then we also use this word critical point. So the difference is when we say critical number, it's the x value, and then when we have critical point, then that is the point. We have x value and then y value. Okay, so if you are asked to find critical point, you are finding both a x and y value. If you're asked to find the critical number, you are just finding the x value. Sometimes people use this like when they say critical point, sometimes they just refer to x value, but in general, usually it means critical number means the x value and critical point means the point. Okay, so now what is the critical point? Critical point or the critical number is the c or x value in the domain of the function. So it must be in the domain of the function at which the derivative is zero or the derivative does not exist. So what this gives us is it gives us all the possible values where the absolute max or absolute mean could occur. Okay, so it gives us a point where we can find the maximum and minimum. So this critical number are the candidates. Okay, critical points are the candidates for maximum and minimum. So basically, critical number means the number in the domain of the function where the derivative is zero or the derivative does not exist. Okay, those two things. So we are going to look at whether the derivative is zero or the derivative does not exist. So those x values are the critical number, and if we find the corresponding y value, then that becomes a critical point. So let's look at some examples here. So we are going to find the critical points here. So the first example, we have f of x equals natural log of x divided by x cubed. So in order to find critical points, so what we do is we'll find the derivative, set it equal to zero. So we will look at two conditions. The first one is where the derivative is zero. Okay. And the second condition, we are going to look at where the derivative does not exist. Those are the two things that we'll look at. Okay, and those values would be our critical points as long as that number is okay, as long as the c values are in the domain of the given function. So let's go ahead and find the derivative of this function. So we are going to use the quotient rule of derivative. I think you still remember that. So f prime of x equals, so this is quotient rule, remember, it's denominator times derivative of numerator minus numerator times derivative of denominator divided by denominator squared. Okay, so denominator is x cubed times derivative of numerator, so it's 1 over x because it's natural log of x, right? Minus numerator, which is, let me erase this, numerator, which is natural log of x, times the derivative of denominator, which is 3x squared, divided by x cubed squared. And that gives us, if you simplify this gives you x squared minus 3x squared natural log of x divided by x to the sixth. Now we can factor out x squared from the numerator. That gives us 1 minus 3 natural log of x divided by x to the 6. So if you simplify this, you get the derivative of that function is 1 minus 3 natural log of x divided by x to the 4th. Now again, we are going to look at two things here. First, let's look at the second point here. Okay, the point of the x value where the derivative does not exist. So if you look over here, does not exist means the derivative is not defined. So if you look over here, when x equals 0, okay, when x equals 0, the derivative is undefined, okay, or the derivative does not exist. So f prime of 0 does not exist. Now one more thing you need to check. So that could be a critical point, okay, critical number, but we need to have that number in the domain of the function. Now you go back and check here, okay? Can we take x equals 0 for that function? It's no, right? Because if we take x equals 0, we'll get a 0 in the denominator also. There's a natural log of x in the numerator. We cannot have natural log of 0. That's the domain of natural log of x is positive x values, right? So that means x equals 0 makes the derivative undefined, or the derivative does not exist at x equals 0, but it's not in the domain of the function, the original function. So we cannot take this as a critical number, okay? Now, that's the only point where the derivative does not exist. So now we go back and use this one. So we are going to find the x values where the derivative is 0. So in order to do that, we take the derivative and we set it equal to 0 and then solve for x. So we have 1 minus 3 natural log of x over x to the 4th equals 0. So if you multiply by x to the 4th on both sides, so you get 1 minus 3 natural log of x equals 0. And then if you subtract 1, you get negative 3 natural log of x equals negative 1. And then divide by negative 3, you get natural log of x equals 1/3. Now, I think you know how to solve this. So if you have log a x equals, say, y, then that changes to x equals a to the y, right? So you know how to solve the log equations. If not, then you need to go back and refresh your algebra. So here we get x equals e to the 1/3. Okay, so that is the critical number. So if you are finding critical point, then you need to find the y value. So in order to find the y value, what we do is we'll take that x value and we'll plug it into our function right here, okay, to find the y value. So what we do is we find f of e to the 1/3. So you need to take that and put it into your original function. So where you get natural log of e to the 1/3 divided by e to the 1/3. And then what will you get? So natural log of e to the 1/3. So you know that if the base and this number are same, so that just gives us 1/3 in the numerator. In the denominator, you have e to the 1/3, or that basically is 1 over 3 e to the 1/3. Okay, so the critical point for that function is just this one. So e to the 1/3, that's the x value, comma, y value is 1 over 3 e to the 1/3. Okay, so that is the critical point. Let me erase this part so that we can do the next question. So now let's look at this question here, the second question that we have. The first thing that we are going to do here is again find the derivative. So derivative of 1 over x is negative 1 over x squared. Okay, and then it does not look like x squared. So negative 1 over x squared, and the derivative of natural log of x is 1 over x. Now again, let's look at the second point, second point that we have here to determine the critical number. So here, where is the point where the derivative does not exist? So the point here where the derivative does not exist is x equals 0. Again, 1 over 0 is undefined, right? But again, for this function, we cannot put 0 here, we cannot put 0 here, which basically means x equals 0 is not in the domain of the function, so we cannot take it as a critical point. So x equals 0, that does not work. Okay, now the second thing that we need to do is find the x values where the derivative is 0. So for that, we are going to take this derivative and then we are going to set it equal to 0. Okay, so negative 1 over x squared plus 1 over x equals 0. So we can just add negative 1 over x squared, so it goes on the other side. So let's go ahead and multiply by x squared on both sides. If you do that, so 1 over x times x squared is just x. 1 over x squared times x squared is 1. So x equals 1 is the critical point. Sorry, critical number. So in order to find the critical point, what we do is we'll take that x equals 1, we'll put it into our function. So f of 1 equals 1 over 1 plus natural log of 1. So we know that natural log of 1 is 0, so that's just 1. So the critical point for this function is x value is 1, y value is 1, so it's 1 and 1. Okay. So now we'll learn how to find the absolute max and absolute mean for the function. Okay. So there are three steps that we are going to do. The first one is we'll find the critical numbers of f in the given interval, in the open interval AB, because we are not going to take those endpoints right now. And then we'll find the value of f at each of those critical numbers. Basically, it means we'll find the critical point. Okay. And then we'll also evaluate the function at the endpoints at a and b, because it's close interval. We are looking for absolute max and mean. So when we consider absolute max and mean, we need to consider the endpoints. So we'll find the value of the function at the critical numbers. We'll find the value of the function at the endpoints. Now we'll compare all those values. The highest value in that list is the absolute maximum. The smallest value in the list is the absolute minimum. So let's look at an example. Say it's a function. So first we are going to find the critical numbers. So for that we need to find the derivative of the function. So let's go ahead and do that. So the derivative of x to the fourth is 4x cubed minus derivative of 4x squared is 8x plus derivative of 2 is 0. So that's the derivative. Now this is a polynomial function, so it means the derivative exists everywhere. So there's no point where the derivative does not exist. So remember those 2 points that we need to consider. First one, f prime of x does not exist. And the second point, f prime of x is 0. Okay, so now the first one, we don't have any point where the derivative does not exist. So we'll move on to the second one where the derivative is 0. Okay, so for that, again, what we do, we'll take this derivative and we'll set it equal to 0, and then we'll solve for x. So we can factor out 4x here. So that gives us x squared minus 2 equals 0. Now from here we can say 4x equals 0 or x squared minus 2 equals 0. So from here we get x equals 0, and then from here we get x equals, so square root of 2, so we have positive and negative square root of 2. So the critical numbers, so now are these functions in the domain? So again, we are not considering the entire domain of this polynomial, right? The entire domain for the polynomial is all real numbers from negative infinity to infinity, but we are just looking at this given close interval from 0 to 2. Now we have critical numbers as 0, square root of 2, which is both positive and negative, but we don't have a negative in our interval. So that's not the point of our interest. Our point of interest, or the interval of our interest, is 0 to 2. So our critical numbers for this interval are 0 and square root of 2. Again, we are not taking the negative because it's not in that interval. Okay. Now the second is, so that's the first and the second step. So we found the critical numbers. So now the next step is we'll evaluate the function at this critical number as well as at the given interval. Okay. So again, sorry, one more thing. This 0 is also not a critical number because it's at the end point. But no matter whether it's critical number or not, we are going to evaluate at 0 because it's at the endpoint. So what we do is we'll evaluate the function at the critical number, which is square root of 2. Okay, so to evaluate that, you'll take this one and put it into the original function. Don't put that in the derivative, okay? Because to evaluate the function, we have to put it into that original function. So square root of 2 to the 4th minus 4 times square root of 2 squared plus 2, and then that equals negative 2. Then we'll evaluate the function at the endpoint. So f of 0, so when you plug in, that is just 2, right? This is 0, this is 0, so it's just 2. And then f of 2 is 2 to the 4th minus 4 times 2 squared plus 2, and that also gives us 2, right? So it's 16, yeah, 2. So now we have absolute minimum clearly at this point here. This is the absolute minimum. So absolute minimum, absolute mean is negative 2, and it occurs at x equals square root of 2. Okay, and then absolute max, we have two absolute max, that is 2. So one occurs at x equals 0 and the other one occurs at x equals 2. So we have two absolute max. And again, this is only in that given interval. It's not for the entire domain because this function goes from negative infinity to infinity. So we really cannot find the absolute max or mean in the entire domain because it goes to the infinity on both directions, right? So we need to have some specific interval where we are going to look at the absolute max and mean. So let's look at another example. Again, we are going to go ahead and find the derivative of this function first. G prime of x. So now we have to use the chain rule here. So derivative of natural log of x plus 2 is 1 over x plus 2 times, we need to find the derivative of inside function. So in this case, it's just 1, right? And then the derivative of 1 over x is negative 1 over x squared. Okay, now again, we are going to look at two things. The first one is where the derivative does not exist. And the second one, where the derivative is 0. Okay, so the first one, if you look at this function, derivative is, the derivative does not exist at x equals 0 because you cannot plug in x equals 0 right here, right? But x equals 0 is not in the domain of the function, or domain of, it's not in the interval, given interval. It's not in the domain, but also it's not in the given interval, right? Now, the other point that makes this derivative undefined is x equals negative 2, because if you put negative 2 here, then that makes 1 over 0, which is undefined. So the derivative does not exist at x equals negative 2. But again, that is not in the given interval. So we are only looking at the values for the x values from 1 to 5. So none of these are in that interval. So we are not going to take those points. So now all we need to do is we set the derivative equals to 0 and then solve for x to find the points where the derivative is 0. Okay, so let's go ahead and do that. So we have 1 over x plus 2 minus 1 over x squared equals 0. So we can add 1 over x squared, so that we get 1 over x plus 2 equals 1 over x squared. Now, the easy way to solve this one is just to cross multiply that. So x squared equals, if you cross multiply, 1 times x squared is x squared, and then 1 times x plus 2 is x plus 2. Now bring both of this on the left hand side, so we get a quadratic equation. Now we can solve this equation by factoring. So we have x minus 2 times x plus 1. That's how you can factor that, and that gives us x equals 2 and x equals negative 1. Again here, just be careful because this x equals negative 1 is not in the interval of our interest. So we are not going to take that as a critical number. So the only critical number is x equals 2. So the second step of this process is we'll evaluate the function at the critical number and at the endpoint. So let's go ahead and do that at the critical number, which is 2. So g of 2 is natural log of 2 plus 2, plus 1 over 2. And then if you put it into the calculator, so that's approximately 1.886, okay? Now we need to evaluate the function at the endpoint. So g of 1, so the first left endpoint is 1 here in that given interval, okay? So that is natural log of x plus 2 means 1 plus 2 plus 1 over 1 is this 1. And then if you put it into the calculator, so that's approximately 2.0986. Now similarly, we'll evaluate the function at the other endpoint, which is 5. So natural log of 5 plus 2 plus 1 over 5, and approximately that's equal to 2.146. Now clearly, you can see that we have the absolute minimum. The smallest number here is 1.866, so that's the absolute mean, and the largest number is this one, so that is the absolute max. Okay, now let's see one more example that involves trig function. So now again it's the same thing. We'll go ahead and find the derivative. So we need to look at where the derivative does not exist, and the second one where the derivative is 0, and then we are looking at this interval negative pi to pi. Okay, so let's go ahead and find the derivative of this function. So derivative of x is just 1, then minus, so 2 is a constant here, coefficient, and then sine x, the derivative of sine x is cosine x. Now cosine function is a continuous function, so there's no point where the derivative does not exist. Okay, so it exists everywhere in that interval. So what we are going to do is we are going to use the, so this does not apply here, so we are going to look at the second point here where the derivative is 0. Okay, so we'll take the derivative and then we'll set it equal to 0, and then we solve for x. So now subtract 1, so it gives you negative 2 cosine x equals negative 1. Then divide by negative 2 on both sides, so it gives you cosine x equals 1/2. Now if you look over here, we are looking from negative pi to pi, means we are making a complete rotation going from negative pi to pi. Okay, now cosine x is 1/2 here in the first quadrant, positive 1/2, so first quadrant and the fourth quadrant. In the first quadrant, the value is pi. You can look at the unit circle, pi over 3. And the fourth quadrant, again, be careful. We are going from negative pi to pi. So the angle must be in that range. So instead of taking the angle here and the larger value, we'll just take that as negative pi over 3. So we go from this direction, okay, in that direction, because we go from negative pi to pi, okay. So basically, the x values are pi over 3 and negative pi over 3. So x values are negative pi over 3 and then pi over 3. So now all we need to do is we need to evaluate the, so these are the critical numbers. So we need to evaluate the function at the critical numbers and at the endpoint. So let's go ahead and do that. So h of pi over 3 is pi over 3 minus, again you are going to plug it into the original function, so 2 sine pi over 3. So at this point you can just put it into the calculator, and that's approximately equal to 0.68485. Similarly, the other critical point is negative pi over 3, so negative pi over 3 minus 2 sine negative pi over 3. Again, put it into the calculator. Make sure it's in radian mode. We are not going to use degrees here. Okay, so negative 3.14159. Okay, then h at this negative pi is, oh, I made a mistake here. Did I? Negative pi over 3. Oh, this is, I made a mistake here. At negative pi over 3, it should be 0.68485, and actually the first one should be negative. So it should be negative at pi over 3. And then at negative pi, so we put it into our function. So negative pi minus 2 sine negative pi, and that is negative 3.14159. Okay, and then at pi we have pi minus 2 sine pi, and that's equivalent to 3.14159. So now if you look at this, the highest value here is this one, so that's the absolute max, and then the lowest value is this one, negative part of it, so that's the absolute mean for this function. So now I think you know how to find absolute max and mean. So basically we do two things. First we find the derivative, and then look at two things. And for that derivative, the first one is look at a point where the derivative does not exist, and the second point is look at the point where the derivative is 0. So once you do that, you get those critical numbers, and then you are going to evaluate the function at all those critical points, critical number, as well as at the end points of the given interval. Okay, so here is a question for you to try. You can pause the video and try these questions, and then come back and check your work. Okay, so you can pause the video, do that problem, and come back. I'm going to do it now. So the first thing, again, we are going to find the derivative of that function. So negative 1/4. So it's x to the 8/3. So we bring 8/3 here. X to the 8/3 minus 1, which is 5/3. Then plus 4 times. So we bring that 2/3 here. So 2/3 x to the, so 2/3 minus 1 is negative 1/3. Okay, let's go ahead and simplify this a little bit. So f prime of x equals, so when you simplify this one, you're going to get negative 2/3 x to the 5/3 plus, so this is 8 over 3, and we can bring that down here just to keep that exponent positive. Okay, so now this function is undefined at x equals 0, because if you put x equals 0 here, so this function, this derivative is undefined at x equals 0. And then if you look over here in the interval, 0 is in that interval. So basically that means our, so f prime of 0 is undefined or does not exist, right? You can also write does not exist at this point. So basically that means one of our critical numbers is x equals 0. So we found one. Now the next one is we'll set the derivative equal to 0. So we'll take that derivative, which is this one. So negative 2/3 x to the 5/3 plus 8 over 3x to the 1/3 equals 0. Okay. Now we'll take this quantity right here on the right hand side. Since it's negative, we'll move that on the right hand side. So we basically get 8 over 3x to the 1/3 equals negative 2/3 x to the 5/3. So let's go ahead and do this. Let's go ahead and multiply by x to the 1/3 on both sides. So if we do that, we get 8 over 3 equals, sorry, this is positive, okay, 2/3 x to the, so when you multiply by x to the 1/3, that becomes x squared here. Okay, and then we can just multiply by 3, you know, to cancel that 3 and that 3. So if you multiply by 3 on both sides, that gets canceled. So we have 2x squared equals 8, or if you divide by 2, you get x squared equals 4, or that gives us x equals positive and negative 2. Since negative 2 is the endpoint, we don't consider that as a critical number, but still we will evaluate the function at that point. Okay, so basically our critical numbers are, so let me write them down here. Okay, so our critical numbers for this function, critical numbers are 0 and then uh, just 0. Actually, -2 is over there. We cannot take 2 because it's not in the interval. So just the critical number that we are going to consider for absolute finding absolute max and mean is just 0. And then we'll evaluate the function at the endpoints. Okay. So let's go ahead and evaluate the function at 0. So if you evaluate the function at 0, it just gives you 0. And if you evaluate the function as at -2, so that's -1/4, -2 to the 8th third, and then plus 4 times -2 to the 2/3, and then if you put that into the calculator you get 4.7622, and then we'll evaluate the function at 1. It's -1/4, 1 to the 8th third plus 4 times 1 to the 2/3, and then if you simplify that you will get 3.75. So clearly you can see here that this is the maximum value, that's the absolute max, and the minimum value is 0, so that is the absolute mean. Okay, and that's all for this video. I'll see you again in the next video.